So I'll be telling you today about some results that are motivated by the field of statistical optimal transport. I want to tell you in particular today about the problem of estimating optimal transport maps when you have two distributions that are unknown, but you observe IID samples from these distributions. How can we estimate the underlying map? And answering this question leads to constructions of stochastic optimal transport maps, which are sometimes a little bit subtle to characterize their fluctuations, which is of interest to statisticians. And I want to tell you about some of our results in this area and how they lead to maybe questions of standalone interest in the general area of stability of optimal transport maps, questions that have been studied in many other communities in this room. So everything I tell you today is going to be based on joint work with three wonderful collaborators. Siva Balakrishna and Larry Wasserman were my PhD advisors when I was at CMU. And Jonathan Alsweed is a long-term collaborator. He's faculty at New York University. So let me start with just some very high-level motivation for kind of the practical motivation for the results that I'm telling you about today. As we know, there have been many recent data analytic applications of optimal transport in a variety of areas, both statistical, machine learning, and also scientific areas. And broadly, there are two types of these applications. On the one hand, there are applications where optimal transport arises as a methodological tool. This was, for instance, the case in the talk that we just heard by Yao, where optimal transport maps may arise as a means towards an end of generating new samples, and we may use optimal transfer maps to map a noise to an output distribution that we may be interested in. There are many other applications where optimal transfer is really used as a methodology. And then there are other applications where optimal transport objects really form the main object of interest, where they really model some scientific phenomenon that we may care to be studying. This is, for instance, the case in applications that many of you know of in trajectory inference, in developmental cell biology. There are many other instances of this. And one of the broad goals of the field of statistical optimal transport is to make sense of how can we estimate optimal transport objects motivated by these kinds of applications. And especially in the second category, the category where optimal transport maps form the main object of scientific interest, it's often very relevant to ask the question, how can we actually quantify the uncertainty of our estimates of the optimal transport map? If I'm giving a scientist an optimal map as the final object of study, they may want to know what is the statistical uncertainty of this object. And that's one of the types of questions that I'll be talking about today. So I'll be talking about broadly estimation of optimal maps from data and how can we quantify the uncertainty, the statistical uncertainty of these objects. Okay, so I'm going to adopt a very idealized problem setting just in order to give you a sense of the kind of theory that we can say about these problems. This is going to be a much simpler problem setting than needed. Our results are somewhat stronger than this, but I just want to give you the main idea of what's going on. So throughout the talk, I'm going to assume that P and Q are two absolutely continuous probability distributions, and I'm going to work over the torus for simplicity. So the torus is convenient in that it's a compact set, but it also doesn't have a boundary. This allows us to make some sharper statements with simpler modeling assumptions and allow me to present these results in a simpler setting. Some of them were able to extend to general Euclidean domains. Others, at the moment, we're only able to state over the torus. And I'll indicate when we have extensions. So the object of interest in this talk is going to be the Monge optimal transport map with respect to the quadratic cost with respect to the natural metric on the torus, which I represent by D sub torus over here. In case you haven't worked with the periodic optimal transport problem before, this shares surprisingly many qualitative features with the usual Euclidean optimal transport problem. It can be shown that the solution to this problem, which is a map from the torus into itself, if you extend it to RD via periodicity, it is still going to be the gradient of a convex function, just as in the usual Brenier theorem. So if you're not familiar with periodic optimal transport, you can just think of everything as being the same as usual Euclidean optimal transport. And here's the setting. I'm going to think of P as being, and this is again a simplified setting, I'm going to think of P as being a distribution that I have access to. Maybe if we're thinking of Yao's application, P could have been this noise distribution that was chosen as a Gaussian, some distribution that I know. Q would be some target distribution that I may not have access to. This could be the distribution of the set of images of cats or something of this kind. So I'll think of P as known, Q as unknown, and I'm going to assume that we have access to IID observations from this target distribution Q. And again, a lot of what I say also extends to the case where P is unknown as well, but for simplicity, let's just assume this for the time being. And here are two high-level statistical goals that I'll be talking about today. The first is the estimation problem. The first question is going to be, how can we construct an estimator of T0? By an estimator, I mean a vector field from the torus into itself, which does not require knowledge of Q, since that's an unknown distribution. It's a vector field that only depends on this data that I observe from Q and on the distribution P that I know. So this is going to be a random vector field, and I want it to be a good approximation of T0, even though I don't know what Q is. So that's going to be the first question of how can we construct such an estimator. And the second question is going to be how can we quantify the uncertainty of this estimator? And there are many ways of formulating that. One way is to formulate it in terms of what statisticians would call a pointwise confidence band. And so what am I going to look for over here? I'm going to ask, can we find a sequence of real numbers a n of x, which satisfy the property that t hat n is only going to differ from t0 by a n of x with some prescribed probability. 0.95 is an arbitrary number. You could put whatever you wanted over there, but let's say 0.95. And this is an exact equality. I don't want an inequality. I want a precise confidence interval for t0 of x. So one might ask if you can come up with a statistical uncertainty set of this type. And the traditional way that statisticians construct such objects is by deriving central limit theorems, or by finding other means of characterizing what is the distribution of this stochastic optimal map. If I knew the distribution of t hat n, I could simply look at its appropriate quantiles and I could construct a set of this type. Okay, and so the two main results that I'll tell you about today are first, a rate of convergence for a certain class of estimators for estimating t0, and then a central limit theorem for that class of estimators, which will allow us to obtain sets of this type. And both of these questions, as I mentioned, will lead to some questions of stability of optimal transport, which I'll try to highlight along the way. Let me just briefly mention that a lot of these questions have been studied to great extent in recent literature in statistical optimal transport. In particular, the problem of estimating optimal transfer maps is very widely studied by now, especially in the last 5 years. And the main takeaway I want you to take from this is that there are many different types of estimators that one could cook up for this problem. All of them are stochastic optimal transfer maps or approximations thereof, and they all lead to interesting questions of how you characterize their fluctuations. I'm specifically going to talk about this class of estimators called plug-in estimators. The question of uncertainty quantification is somewhat less studied. I've given here 3 examples of special cases or variants of optimal transport where people have thought about central limit theorem questions of the type that I'll be discussing. But for the most part, in the absolutely continuous setting that I'm describing, there's been relatively little prior work. And there are some recent surveys on all of this literature. I'm sure many of you know the recent book by Sinho Chui, John Niles-Weed, and Philippe Rigolet on statistical optimal transport. We've also written a recent survey specifically on optimal map estimation. Okay, so here's the estimator that I want to study in this talk. It's what I call a plug-in estimator. And it's going to be defined as follows. So remember, we have a source distribution P, which I treat as a known probability distribution, absolutely continuous on the torus. And Q, again, was unknown. We had access to ID observations Y1 through Yn from Q. I'm going to start by forming their empirical measure, defined in the usual way, as the most natural first-order approximation of Q. And then I'm going to mollify that empirical measure using a mollifier K. So K is going to be a mollifier. I'm going to assume that it has sufficiently high order moments in order for it to have good approximation theoretic properties. In some cases, K needs to have more than 2 moments that are equal to 0. And in that case, you can't take K to be, for example, what you might want to take it to be, like a Gaussian. It has to be something that takes on negative values. And so there's a little bit of bookkeeping that one needs to do in order to make sure that this convolution actually defines a bona fide probability distribution. That's some bookkeeping that I'm not going to get into in this talk, but you should just trust that one can make sense of this object with sufficiently high probability. And K sub Hn is just going to be the mollifier now taken with bandwidth Hn. And my plug-in estimator, the object of interest, is going to be defined as the unique optimal transfer map which pushes forward P onto this mollified empirical measure Q hat n. And again, there's some bookkeeping needed to make sure that Q hat n is a valid distribution. And when it does define a valid distribution, this is a well-defined object. There's a unique map from P to hat Q because P is absolutely continuous. It's worth contrasting this object to a different object, which might be more familiar to many of you, one which is maybe a more canonical object of study if you're a probabilist. A different object you might have looked at is just the optimal map that takes P onto the empirical measure Qn. And again, this is an object that has been studied a great deal in the probability literature. It's closely connected to the problem of optimal matchings. And in fact, what I call hat T over here, this mollified version of the empirical optimal map, has actually been used as a technical device to study this empirical map. And I'm going to come back to this literature a little bit later on in the talk. It served as a motivation for some of what we're doing over here. So if you're a probabilist, the empirical map is a very natural object. But if you're a statistician, it turns out that this hat T is a much more natural object, because as soon as P and Q satisfy some regularity, it turns out that this object is a much better approximation of the true map than the empirical 1Tn. So it turns out that mollification will give us better rates of convergence, and I'll explain that as we go along. So, but that's the motivation why we look at this object, not the empirical map. Okay, and so here's the first result, which is going to tell you what is the accuracy of this estimator. And I'm going to work under what I call the Caffarelli assumptions. I'm going to work in maybe the simplest setting that you might hope for optimal transport. I'm going to assume that the densities P and Q satisfy sufficiently many regularity conditions for the true optimal transfer map T0 to be smooth. And what we know from the classical regularity theory by Caffarelli is that it suffices to assume the following conditions. I'm going to assume that the measures P and Q have densities which are Holder continuous with Holder exponent S positive. And I'm also going to assume that the densities are bounded from below over the torus. Okay, and under these conditions, it's known that T0 is going to be of an order of smoothness, which is S plus 1. And here, I'm writing all of this qualitatively, but you'll understand in all the results that I state, the implicit constants will depend on the actual lower bound that's achieved over the torus and the actual Holder, the Holder moduli. Okay, and here's the first result on what is the rate of convergence of this T hat when we work over this parameter space. So I'm assuming these are lowercase p and q are the densities of the measures P and Q. I'm assuming they're positive, they're S Holder smooth, and I'm going to pick the bandwidth of that mollifier in a very particular way. Notice, first of all, that it's vanishing. So I'm not trying to estimate the mollified version of the true optimal map. I really am estimating the true optimal map. This is a vanishing amount this is a vanishing bandwidth. I choose it on the order of n to the minus 1 over d plus 2s. So the bandwidth will be larger as there is more smoothness. And I'll come back to its choice in a second. Under these conditions, this is the rate of convergence of the estimator that I showed you on the previous slide. And so before I interpret it, let me just say that this is a rate of convergence that has appeared before in the literature. At the time when we proved this result, this upper bound was only known to be achievable by an estimator due to Tudor and Rigolet, which was computationally intractable. It was a theoretical construction that they had, which achieved this. And at the time when we proved this, this was the first estimator which achieved that upper bound using a computationally tractable estimator. But now let me tell you what this rate is saying. And let's focus first on the case where the dimension is equal to 3. The way to interpret this rate is to think of the two extremes of smoothness, when the smoothness is very close to 0 or when it's very close to infinity. On the one hand, when the smoothness is very close to 0, and in fact, there is a sense in which you can actually take S to be 0 in this result with the appropriate bookkeeping, this vanishes and I get a rate of n to the minus 1 over d. That's a rate that many of us have seen before. And in fact, this overall rate of convergence actually matches the rate of convergence in the famous Ajtai-Komlov-Shtusnadi optimal matching theorem. It's n to the minus 1 over d when the dimension is large enough. It is n to the minus half in dimension 1, and there's a logarithmic correction that appears in dimension 2, which actually matches exactly that AKT optimal matching theorem that many of you might know. So when there's no smoothness, estimation of the map coincides with the rate of convergence of the empirical measure under the Wasserstein distance. On the other hand, once you assume some smoothness, this rate formally approaches the rate n to the minus half. Right, if both s are going to infinity, this 1 over d kind of washes out, and I get a rate that looks like n to the minus half in all dimensions, up to a small polynomial factor. Okay, and so what we see is that we basically approach the rate of convergence that appears in the central limit theorem, a very fast rate of convergence that is not dimension-free once you have a lot of smoothness. And this is the kind of phenomena that the empirical map that I mentioned on the previous slide would not be able to achieve. You really need this mollification in order to achieve this kind of result. And again, you can kind of see that by kind of looking at this bandwidth. When there's very little smoothness, this bandwidth is basically n to the minus 1 over d. N to the minus 1 over d is the typical distance between points in RD when sampled from an absolutely continuous measure. If I'm mollifying at the bandwidth n to the minus 1 over d, I'm essentially not mollifying. I'm essentially putting a bump at every point. I'm not essentially doing any smoothing. And that is kind of suggesting that the empirical map would achieve this when the smoothness is very low. However, once there is more smoothness, mollifying gives you a big advantage. You're actually mollifying on a wider range. smoothing many points together, and that gives you this faster rate of convergence. Good. So let me tell you just briefly how one proves this result. Roughly what we're doing is we have an optimal map T0 from P to Q, and we said, okay, we don't know Q, we're going to estimate it using some underlying measure, this Q hat, this modified empirical measure. And now if you want to prove an upper bound on the L2 error of T hat to T0, basically what you're asking is, I've perturbed the target measure in my optimal transport map, and now I want to ask how much did the optimal map change as a result of this perturbation. And we know from textbook results that optimal maps are stable qualitatively under perturbations of the underlying measures in the weak topology. That's a classical fact. But what you would want in order to prove the result I had before is really a quantitative analog of that fact. That quantitatively, can I say that if the target measure is changing, the optimal map will be controlled in L2? And this, of course, is a question that has been of interest more broadly in the community. And a question that you might ask, and what has been asked before, is does one expect a bound of the following type to hold? In principle, one could ask for different metrics on the right-hand side than the Wasserstein distance, but the Wasserstein distance is actually on a similar scale as the left-hand side, so this is maybe a morally natural target to look for. So is there a modulus of continuity, an exponent alpha for which an upper bound of this type holds? And as many of you know, this question was first studied by Gigli in 2011, based on a result that was communicated to him by Ambrosio. And what he proved is that if the map T0 is Lipschitz, then one can actually take alpha to be 1/2, that one indeed has this kind of quantitative stability with a 1/2 Holder exponent on the right-hand side. And again, as many of you know, there was also some follow-up work, some really beautiful work by Delalande and Merigot, which was then followed up by many others, Cyril Letruy in particular, who has written a beautiful set of course notes on this subject, where they proved something different. Rather than placing assumptions on the map in the way that Gigli did, they instead placed assumptions only on the source measure, allowing the target to be arbitrarily irregular, and therefore allowing for maps which may in principle be discontinuous. And what they proved is that even if you only have such assumptions on the source measure, one can get this result with a Holder exponent of 1/6. Okay, and what we proved is a third result in this direction, one which makes, again, different assumptions than the last two results, but arrives at a stronger conclusion. We proved a result that's more similar to Gigli's. We said, let T0 be not only Lipschitz, but actually by Lipschitz. So let's assume its inverse is also Lipschitz. Then what we were able to show is that you actually get this with an exponent of 1. And that's what led to the result I had on the previous slide. So this is the formal result. And I'm stating it over the torus just to be consistent with what I've said so far, but this actually holds more generally in Euclidean space, exactly as it's stated. And so the result is, if the map T0 from P to Q is by Lipschitz, and you give me any measure Q tilde, it doesn't have to be absolutely continuous in particular, then the optimal transfer map from P to Q tilde is going to differ from the optimal map T0 in L2P by at most a multiple of the Wasserstein distance between Q tilde and Q. And the implicit constants in this result are dimension free. They depend only on the Lipschitz modulus of T0 and that of its inverse. And in a linear way from those quantities. Okay, so one has a linear stability, a Lipschitz stability bound between these quantities when you have this by Lipschitz assumption. And we wrote a paper a few months ago where we actually showed that this kind of result extends even to the case where you're perturbing both the source measure and the target measure. In this case, one has to be a little bit more careful with what this L2P means, because now the supports of P and its perturbation could be different. So the result looks a little bit different, but qualitatively, it gives a very similar answer. Yes? I couldn't hear you. There's no assumptions on P. P needs to be absolutely continuous, and the map needs to be by Lipschitz, but P could, in principle, be arbitrarily irregular beyond that. Yeah. So it could be something that has like a vanishing density in some places, something that really violates Caffarelli's assumptions, but then if I push it forward through a nice by Lipschitz map, whatever I get on the other end, I'll call it Q, and then I could take P and Q to be related in that way, and this result would hold. Yeah. Thank you for the question. Or another example by Caffarelli's contraction theorem, right? This is telling you that if, and again, this holds over RD. So if I take P and Q to be two strongly log concave measures, then I get this kind of Lipschitz stability bound where Q tilde could be any perturbation of one of the two strongly log concave measures, and that perturbation need not lie in the strongly log concave class. It can be a perturbation of arbitrary type as long as it's controlled in Wasserstein distance. Okay. Any other questions? Okay, so okay, and so I should say that once you get to this point, you can analyze the estimator that I had on the previous slide by simply saying, what is the rate of convergence of that mollified empirical measure under the Wasserstein distance, which is a question which is much more tractable to answer. When you're in the regime of the result I had on the previous slide, the Wasserstein distance is actually equivalent to a negative Sobolev norm. And once you can relate this to a norm between the underlying densities of these objects, it becomes a simple calculation of what is the approximation rate of convolution under this type of norm. And so these are questions that one can answer pretty tractably. So the high level picture is that we had a statistical result on the previous slide. It relied on this deterministic stability bound. Now I want to give you another pair of results of the same type, to the extent that I have time, where I'm going to first give you a central limit theorem, statistical result again for this plugin estimator. And that statistical result, that central limit theorem, will come again from a deterministic bound. It's one which is essentially a strengthening of this result. It'll be, rather than a quantitative stability bound, it'll be a quantitative linearization bound. I'm going to say somehow that this gap is well approximated by some operator in a quantitative sense, and that operator will be linear. It's one from which we'll get a central limit theorem. So that's on a high level where I'm going. Okay, so here's the central limit theorem. And I will be making somewhat stronger assumptions in this part, so we'll get stronger results under slightly stronger assumptions. And the main assumption that I'm changing is that I'm assuming that the smoothness is greater than 2 in this case. And the central limit theorem looks different in dimension 3 versus in lower dimensions. So let me start with the high dimensional case. So I'm assuming, as before, that the densities P and Q are S-Holder smooth. I'm assuming that they're positive over the torus. And I'm again going to place a condition on the bandwidth. Just to remind you from the previous result, n to the minus 1 over d plus 2s was that optimal scaling of the bandwidth for which I got that rate of convergence that I told you before. One can show that if you go above or below that rate, there's a bias variance kind of trade-off happening. And if you go above or below that rate on the right-hand side, you get a slightly suboptimal rate of convergence. And I'm going to put myself slightly below that rate in this result. And the reason I'm doing that is because on this side of that bandwidth, the bias of t hat is going to be slightly smaller than its variance. And I want a central limit theorem that's actually centered at the true population object, not centered at its bias. That's the reason I put myself arbitrarily close, but below that optimal scaling of the bandwidth, n to the minus 1 over d plus 2s. That's the upper bound. On the lower bound side, I'm placing myself polynomially above n to the minus 1 over d. And remember from what we said before, n to the minus 1 over d is kind of the scaling where smoothing isn't really doing anything. It's just putting a bump at every point that I observe in the sample. By putting myself polynomially above that, I'm ensuring that there's a non-trivial amount of smoothing. And in that case, the mollified empirical measure is actually a smooth density with high probability. And that's a key to being able to obtain a result as strong as what I'm about to state. Under the scaling of the bandwidth, this is the result that one gets, is that, so I should say from the outset that by even evaluating these things point-wise, there's some bookkeeping that needs to be done, right? The way I defined t hat n was an optimal map from P to Q hat. In order for me to be able to evaluate it, this in principle is an L2 well-defined object. There's no reason why I should be able to evaluate it point-wise. So there's some bookkeeping in even me just being able to write this statement. And that bookkeeping can be done exactly under this condition, which ensures that Q hat is a smooth enough object. And with high probability, the map T hat n will itself be smooth, continuous, and I can evaluate it point-wise. So that's happening under the. Okay, and under that assumption, or under these bandwidth assumptions, this is the central limit theorem that one gets, is that in the point-wise sense, this plug-in estimator is going to be asymptotically normal. The scaling that's happening over here is such that you can trust me that if you plugged in the optimal choice of bandwidth, this scaling would be exactly consistent with the rate of convergence that I had shown you on the previous slide. So it's somehow the natural scaling of the central limit theorem. And this converges to a Gaussian with some multivariate Gaussian in dimension d. And we can give an explicit expression. It's a little bit of a complicated expression, but I will interpret it for you. We can give an explicit expression for what the limiting variance is. It depends on the Fourier transform of the kernel that was used to mollify the empirical measure. It depends also on, okay, I haven't defined these, but these are like the Brenier potentials associated to T0. The details of this expression don't matter, but maybe the way to read it is as follows. This matrix M is some positive definite matrix. Between friends, let's say it's the identity. So I'm ignoring these M of X's everywhere. And let's say I just think of the diagonal entries of this matrix. I'm going to get some psi squares over here. I have some psi squares down here, which are squared, so I get some psi cubes. If you do the right bookkeeping between all these quantities, what you're going to see is that this object basically looks like a negative Sobolev semi-norm of the kernel. So I have the Fourier transform squared. It's going to end up being divided by the right power of psi, such that this looks exactly like this times the identity. I should say it's dominated by this in the positive semi-definite order. Okay, so what you're seeing is that somehow in a pointwise sense, this estimator is on the scale of a negative Sobolev semi-norm of the kernel. And this is somehow consistent with the L2 results that we had earlier, right? Earlier, I was saying that the L2 norm of T hat depends linearly on the Wasserstein distance between Q hat and Q, which in turn is on the order of a negative Sobolev norm. So that was somehow saying in an L2 sense, maps are on the same scale as the negative Sobolev norm of the densities. This is somehow, you should think of it as a pointwise analog of that fact. That in a pointwise sense, this thing looks like the negative Sobolev norm of the kernel, which is on the scale of the densities. Roughly speaking, that's what this result is saying. And let me just also tell you what happens in dimension 2. In dimension 2, we're not able to get as far. And as many of you know, dimension 2 is always the most subtle regime for these kinds of optimal matching problems or this related smooth problem. We're only able to get a central limit theorem at the uniform distribution. And in this case, this is not useful for statistical purposes because it's really just at one pair of distributions. But nonetheless, I want to mention it as a mathematically interesting result, in my opinion, is that we obtain very different phenomena in dimension 2. What we obtain in this case is that under appropriate assumptions on the bandwidth, which I will not discuss, we still get a central limit theorem for this estimator that I described earlier. We can still evaluate this thing pointwise and so forth. I'm centering it at X because I'm assuming P and Q are both equal to the uniform distribution, so the optimal map is just the identity. The scaling in this case is consistent with what we know, that in dimension 2, the scaling should be logarithmic in the sample size. And Hn scales polynomially in n. So this logarithm really scales like log n. But what we find remarkably is that the limiting distribution no longer depends on the kernel, right? We saw that in dimension 3 or greater, we saw the limiting distribution depended on something that was on the scale of the negative Sobolev semi-norm of the kernel, K. If I change the modification, I would get a different answer. Here, we get a universal limiting distribution, the identity divided by 4 pi. And many of you may have seen 1 over 4 pi before in optimal matching problems, and I'll get to that if I have time. So that's an interesting difference in scalings that one gets in dimensions 2 and above. I didn't mention the one-dimensional case, but as you know, that's usually the simpler regime for optimal transport, so I won't go there. At what time am I supposed to end? 7 minutes, perfect. So then I have a bit of time to tell you about what's going on under the hood in the proof and to try to give you a sense of where these different scalings are coming from and so on. Before I go there, are there any questions about the statement of the CLT or anything else? Yeah. I mean, if I'm thinking of statistical practice, what would an L2 CLT allow me to do? It would allow me to get confidence intervals for functionals that are continuous in L2. For example, functionals of the map that are continuous in L2. I could get confidence interval for those. But if I want something stronger, like a pointwise confidence interval for the true map, then an L2 CLT wouldn't allow me to do that. I think it is, but that's not something that we've been able to prove. I should also say though that we actually proved in our paper that an L2 limit law doesn't hold for this estimator. So I think it holds on if you weaken L2 enough under an appropriate negative Sobolev topology. I assume you could prove a weak limit of that type, but in L2 we did prove that it doesn't hold, and that's intrinsically due to the fact that this estimator Q hat itself is not weakly convergent in L2 for the scales of bandwidths that I have in mind in these results, which are the optimal ones from the statistical point of view. Yeah. Oh, sorry.
So in your setting, is it a ton of work to upgrade the CLT to a von Baron-Hussein theorem?
No, that would be doable. A bit like a Berry-Yassine type of result. Yeah. That would be doable in a pointwise sense. So to say that the CDF of this object approaches, like the CDF of the Gaussian in a uniform sense, that would be, we haven't done it, but that would be relatively easy to do. Making the CLT uniform would be a different question. Yeah. Okay, let me just tell you a few elements of the proof before I close. So as I alluded to earlier, our inspiration for the proof of the central limit theorem comes from the line of work on optimal matchings, in particular the AKT theorem and more recent results that many of you are familiar with in the PDE literature. So let me again come back to this rate of convergence and briefly remind you what this is saying, because it'll be useful for what I tell you next. So again, as many of you know, if we look at this different separate problem from what I've been talking about so far, the rate of convergence of the empirical measure under the Wasserstein distance, a widely studied topic, what's known is that if Q has a nice density, for example, it's the uniform distribution on the torus, one is able to very sharply characterize even the logarithmic factors that appear in this rate. This was first done by AK and T in the 1980s. And what they proved was this rate, which again is dimension dependent when the dimension is greater than 3. It's parametric when the dimension is 1, and something else happens in the middle. And just again, to remind you, the way to interpret this rate is that there are local phenomena in high dimension and global phenomena in low dimension that are interacting. In high dimension, n to the minus 1 over d is the typical distance between nearest neighbors of points sampled from an absolutely continuous distribution. Is the typical diameter of a Voronoi cell in dimension d. And so to first order, when the dimension is large enough, the optimal matching between the underlying distribution P and the empirical measure Qn is simply obtained by mapping each Voronoi cell to its centroid in red. That's morally what the optimal map looks like, even though that doesn't define rigorously a transport map. That intuition starts to fail when you're in low enough dimension. When you're in low enough dimension, there are other phenomena that kick in, which actually drive the first order behavior of the map. For example, we know that even in dimension 1, the typical difference between the mean of P and the mean of Qn is on the order of n to the minus half by the central limit theorem. And that's already a slower rate of convergence than n to the minus 1 over d. So you know there must be global phenomena of this type that impede this picture from driving the behavior in low dimension. So local phenomena in high dimension, global phenomena in low dimension, and they interact in dimension 2 to lead to these interesting rates of convergence that have logarithmic corrections. Okay, so this was well known for a long time. And then there was a group of statistical physicists about 10 years ago who asked the question, can we do something sharper? Can we actually ask, if I rescale the empirical Wasserstein distance appropriately in dimension 2, can I actually get the limiting behavior of this object in expectation? And using heuristic techniques, they were able to predict that the limit of this object would actually be 1 over 4 pi. And it was the ansatz that they used in order to arrive at that result, which was the inspiration for what we did. And here's the ansatz that they used. The ansatz that they used is the following. They said, okay, we know that the optimal map in quadratic optimal transport is driven by a solution to the Monge-Ampère equation. And when I'm in their case over here, where P and Q are both close to the uniform distribution, the Monge-Ampère equation linearizes to a Poisson equation. Now, the Monge-Ampère equation does not make sense if I'm actually working with empirical measures as I am over here. It doesn't make sense for discrete distributions. However, the Poisson equation does. The Poisson equation I can make sense of even when the right-hand side lies in a very weak space. And so what they said is, here's the ansatz. They said, maybe the empirical map, which pushes forward Q onto Qn, or P onto Qn, P is equal to Q in this context, maybe even though the Monge-Ampère equation doesn't make sense for this map, even if this thing is highly irregular, maybe there is a sense in which that map is well approximated by the solution to the appropriate Poisson equation, the linearization of the Monge-Ampère equation. That was their ansatz. And they said, if this were to be true, then there should be a sense in which the empirical Wasserstein distance is on the order of this Dirichlet energy, where UN is the solution to this linearized equation. Again, this equation makes sense in a weak sense, even if I have an empirical distribution on the right-hand side. This is appealing. Unfortunately, you run into the fact that this Dirichlet energy is not finite when the dimension is greater than 1, right? If I have the empirical measure does not lie in h to the minus 1 when the dimension is greater than 1. And so because of that, you cannot expect the solution to lie in h1. So this in general is infinity. But if you're a statistical physicist, that doesn't impede you from proceeding, right? There are renormalization ideas in this community that allow you to say, okay, actually, this should be interpreted in an appropriate sense with an appropriate renormalization, and one can still get an answer out of this. And by doing this kind of renormalization, they arrived at this value of 1 over 4 pi, which turned out to be the correct prediction. What was shown a few years later by Ambrosio, Stra, and Trevisan was that this prediction of 1 over 4 pi was correct. And the way they achieved this result was by saying, let's not look at this, but let's instead replace Qn by its mollified version, the same object that I'm working with, but with a very small amount of mollification. N to the minus 1 over d in this context is n to the minus half because I'm in dimension 2. And they said, let's mollify logarithmically more than n to the minus half. So I'm smoothing just a little bit. very, very little bit. So I'm not distorting the empirical measure by much. And they said, if I smooth by this amount, this Dirichlet energy starts to make sense. It starts to be finite, quantitatively so, within the confines of what they needed for their result. And they then showed that the approximation error of doing this is of low order. They made sense of the asymptotics of this thing when you regularize, and they obtained the result, 1/4 pi. On the other hand, what they found is that when the dimension is greater than 3, they tried the same procedure, but they found that they could never get rid of this regularization. They found that the regularization by mollification was always of leading order. And this should remind you of what we saw in our result. We saw that in dimension 2, we got a universal limit. No matter what the mollifier was, my central limit theorem was always had this 1/4 pi as well, no matter what the mollifier was. But in dimension 3, I had a central limit theorem that did depend on the mollifier. This is somehow consistent with the observations that they had in this result. And if you can grant me one more slide, I have just the last slide to connect this to what we actually did to prove that central limit theorem. So if we return to our situation, what can we do with this background? Well, here's what we said. We said, unlike Ambrosio, Strand, Trevisan, who were trying to study the empirical measure and therefore had to work with a regularization that was very close to n to the -1/d, in a regime where the empirical map is a highly irregular object, and one really needs to do some hard analysis in order to study the Dirichlet energies that arose, we have the benefit that we're thinking about a smooth problem where we're actually studying a different object. We're studying this mollified map as the main object of interest. And it was actually the right thing to do in our application to take Hn polynomially larger than n to the -1/d. That was actually the optimal scaling of the bandwidth in our problem. And so using the fact that that's actually the correct nature of our problem, we said, if the bandwidth is large enough, polynomially larger than n to the -1/d, we showed that actually you can linearize the Monge-Ampère equation in a quantitative sense, in a very strong sense, much stronger than the sense of Ambrosio, Strand, Trevisan. And from a PDE point of view, this is a much simpler result. You're really working in the regime where everything is quite smooth, and the linearization can actually make sense of very precisely. So what we showed is that if you look at this map that we carried out of this plugin estimator, its gap is well characterized by the solution to an elliptic PDE, which we can characterize quite sharply when Q hat n is this mollified object. And so basically, this is the approximation that we get. We can sharply say in a uniform sense that this object is well approximated by a linear operator of the mollified empirical measure. And the last word I'll say is that once you get to this point, in order to obtain a central limit theorem, basically it reduces to the question of what are the fluctuations of this object. And that's still a relatively subtle question, because this is, as much as this may be a linear operator, it's a non-local operator. So I'm passing this smoothed object through a non-local operator and then taking a pointwise evaluation out the other end. Still some thought that has to go into this. And I'll just make this final comment about it, which is that the way in which we were able to get limit laws for this object in dimension greater than 3 was using a classical technique that one uses in PDE called constant coefficient approximations. We said that if I freeze the coefficients of this general operator at the point where I'm trying to do my central limit theorem, I can actually, this becomes a simple object to whose fluctuations you can quantify, and that's how we obtained our central limit theorem. However, as we know from optimal matchings, this idea of localizing the problem at a single point is doomed to fail in dimension 2, because in dimension 2, it's not just local phenomena, but also global phenomena that enter the picture. And that's basically the reason why we weren't able to carry out this program in dimension 2. And I think interesting ideas would have to come to bear for that problem. I've gone over time and I apologize for that. I'll stop here. Thank you.